In this video, we will see about the normal incidence related to the electromagnetic waves. So, here we will assume there is a interface or boundary, and boundary is the planar structure, planar boundary, which is separating two media 1 and 2. And these two media are semi-infinite media. Semi-infinite media having the intrinsic impedances eta 1 and eta 2. So generally eta 1 is given by square root of j omega mu 1 by sigma 1 plus j omega epsilon 1. And eta 2 is the intrinsic impedance of the medium 2, that is root of j omega mu 2 by sigma 2 plus j omega epsilon 2. Here mu 1, sigma 1 and epsilon 1 are related to medium 1. Here mu 2, sigma 2 and epsilon 2 are related to medium 2. So eta 1 is this intrinsic impedance of the medium 1. Eta 2 is the intrinsic impedance of the medium 2. And now whatever I am taking, that is the normal to the interface, normal to the boundary. This is the normal. Okay, this is the boundary and this is the normal to the boundary. So I can take here normal to the boundary. Okay, so I can write here. Then this normal is already making 90 degrees with the boundary. Okay, now how to send the incident electromagnetic wave? So incident electromagnetic wave we need to send in parallel with the normal, or this incident electromagnetic wave is sent perpendicular to the boundary. Both are same. Okay, so it is incident by making 90 degrees with the boundary. That's why this is called a normal incidence. Okay, so here EM wave is incident on boundary by making 90 degrees. Okay, or simply we can tell perpendicular wave. So it is a normal incidence. Normal incidence. Okay, so in this particular situation, when the electromagnetic wave is incident normally to the boundary which is separating the two media, what will happen? Is it transmitting into the second medium, or is it completely transmitted into the second medium, or only certain portion of this one is transmitted into the second medium? Then what about the remaining portion? So remaining portion can be reflected. That is what we need to see. Okay, so whenever this is happening, certain portion of the input wave, that means incident electromagnetic wave, will be transmitted into the medium 2 and something will be reflected into the medium 1. Okay, so we have to see the condition for this reflection. Or can we have without any reflection only complete transmission is there, or only reflection is possible without any transmission? All these things we have to see. In general, the main point is whenever if you have the impedance mismatch, impedance mismatch is the important term here. Impedance mismatch is the responsible for the reflections. Okay, is responsible for reflections. Impedance mismatch is responsible for reflections. That is what we need to understand. Okay, then I have taken the boundary here impedance theta 1 and here impedance theta 2 is there. So I have incident some electromagnetic wave perpendicularly to the boundary. Because of the impedance mismatch, whenever eta 1 is not equal to eta 2, then certain portion will be transmitted into the medium 2 and certain portion will be reflected into the medium 1. Okay, about this one we have to discuss. So here if you observe, we are dealing with the three electromagnetic waves. One is incident wave, second one is reflected wave, third one is the transmitted wave. So three electromagnetic waves are available. Three EM waves are available, and in each EM wave we will be having one electric field and one magnetic field. That means three electric fields plus three magnetic fields we have. So we should able to write three electric field expressions, three magnetic field expressions. Later we can able to have what about the reflection, what about transmission we can able to understand. Okay, so for that particular purpose, I'm assuming here perfect dielectrics. Just for easy analysis, we will consider perfect dielectrics. What is the example of the perfect dielectrics is nothing but you can take free space. So in the free space, sigma is equal to 0, which is leading to attenuation constant alpha is equal to 0. So in the electromagnetic expressions, that means electric field expression, and in the magnetic field expression, we will be having the term e power minus alpha z. If you assume z is the direction of propagation, e power minus alpha z is there. But because we are considering the perfect dielectric where sigma is 0, alpha is 0, so that e power minus alpha z will become 1. So now I'm going to write the expressions for the electric fields. So electric field for the incident wave is given by some peak value is available, and because there is no attenuation, e power minus alpha z is 1, and I'm writing the phasor form, you can able to assume like that, so that here e power j omega t will not come. So only e power minus j beta z is available, and I'm assuming that this electric field is oriented in the x direction. So like this, roughly I have written the expression for the electric field, incident electric field. Now I have to write incident magnetic field, reflected electric field, reflected magnetic field, transmitted electric field, and transmitted magnetic field. All these things I have to write. But before writing this one, I need to assume something. What is the direction of propagation? What is the orientation of the electric field? What is the orientation of the magnetic field for the three cases? Okay, that means for the incident, for the reflected, and for the transmitted electromagnetic waves. So all these things are to be considered. Okay, so anyhow, by here, because of the minus z, I can able to tell the direction of propagation is positive z direction only. So those conditions I will take here. Direction of propagation for the incident wave is positive z. Direction of propagation for the transmitted wave is also positive z. But the reflected wave itself, the meaning itself is it is moving opposite to the incident wave. That is nothing but for the reflected wave, the direction of propagation is the minus z. So this is the direction of propagation. Then I'm assuming that electric field is oriented in the x direction and magnetic field is oriented in the y direction of the incident wave. So I'm taking here suffix is I. Okay, so that the orientations of the electric field and magnetic field are x cap and y cap respectively, and direction of propagation is positive z, so that here I'm satisfying all the conditions related to the transverse electromagnetic wave. Then now I will draw the diagram, then we can able to understand what are the orientations of the electric field and magnetic field for the reflected wave and transmitted wave also. Okay, so I'm taking the diagram once again. See here carefully. So this is the boundary, as I said earlier. We'll assume this is the x-axis, and normal to the boundary is the z-axis. That is the direction of propagation. And here we will be having the positive y is coming out of the screen. Okay, so like this we have taken x, y, z is perpendicular to each other, and the screen itself is nothing but xz plane, and the y-axis is coming out of the screen. This is what we have taken. Now the incident wave is moving in the positive z direction, but electric field is oriented in positive x direction. So you see here electric field, here x cap, x axis is there, so that I have to take incident electric field is available in the x direction. That is what I have to follow. Okay, so here I can take incident electric field. So using your right hand three fingers, thumb, forefinger and middle finger, you can able to estimate what is the direction of the magnetic field. These three must be mutually perpendicular to each other. So you can take your right hand thumb in Z direction, so that right hand forefinger will be in the X direction, then automatically your middle finger of the right hand will be indicating coming out of the screen. That means that will be indicating the Y. So that itself is a HI, that means incident magnetic field. So this is the direction of propagation. Okay, so you have to try this one. Okay, while I'm telling you have to try this one, what you need to try means you need to keep your right hand thumb in the Z direction and right hand forefinger is in the X direction. Automatically your right hand forefinger will be indicating coming out of the screen. That means that will be in the Y direction. So electric field is oriented in the X direction, magnetic field is oriented in the Y direction, and direction of propagation is in the positive Z direction. That is what we have taken here already. Okay, now about the transmitted wave we will take. So because of the normal incidence, the transmitted wave will also be having the same rules. That means the transmitted wave will be having the direction of propagation is in the Z direction only, and the electric field of the transmitted wave is also indicated in the positive X direction, and this magnetic field of the transmitted wave will be indicated in the positive Y direction. Again, you can check using your right hand three fingers. Okay, so there are no changes in the orientations of the electric fields and magnetic fields and the directions of the propagations of the incident wave and the transmitted wave. It is easy. But when you try to understand about the reflected wave orientation, so we'll assume that there is no change in the orientation of the electric field. This is a assumption. Okay, so assumption that ER is in positive X direction only. Okay, but it is a reflected wave. That means it has to travel in the negative Z direction only. That is what we have to take compulsory. Then only it is called a reflected wave. So reflection is in the negative Z direction, but I'm assuming that the electric field is not changed its orientation. That means the reflected electric field will be indicated in the positive X direction only. At this particular moment, now we have to give the orientation of the magnetic field. How it is possible? In order to know this one, you have to use your right hand again. Okay, so right hand thumb you have to keep in the negative Z direction, and right hand forefinger should be indicated in the positive X direction. Then in which direction your middle finger of the right hand is indicating? It is going into the screen. That means it is going in the direction of the negative Y axis. That's why I am using here cross circle. Okay, so that I have to take here dot circle for the HI, dot circle for the HT, because those two are available in the positive Y direction. But here the HR, the magnetic field of the reflected wave, is going into the negative Y direction. That means going into the screen. That means the cross circle I have to use. Okay, so if you understand this particular diagram, the topic is very easy. Now I'm going to write the expressions for the electric fields and the magnetic fields here. Okay, so already I have written the electric field of the incident wave. Once again, I will write that one. So I'm taking here incident electric field. I know its orientation is the X cap and it is traveling in the negative, positive Z direction. So beta Z, but it is available in which medium? Medium 1 or medium 2? It is available in the medium 1. Reflected wave and incident wave are available in the medium 1. Transmitted wave is available in the medium 2. So this beta 1 we have to use. The suffix is 1 is required for the beta, because beta is actually coming from omega root of mu epsilon. So mu and epsilon are different for the medium 1 and medium 2. So if you take here mu 1 and epsilon 1, it will become beta 1, and beta 2 is equal to omega into root of mu 2 into epsilon 2. So this beta 1 is to be used for the incident wave and also for the reflected wave, but beta 2 is to be used for the transmitted wave because it is available in the medium 2. So then the peak value of this particular signal I am taking as the ei naught, and as I said earlier, there is no attenuation we are considering here, so e power minus alpha z will not come, and I did not write e power j omega t also. For this particular concept it is not required. If you want you can able to keep the e power j omega t also, but I am working with the phasor, so it is enough. Okay, then I am taking hi. So hi is equal to, I have to write the peak value is hi naught, and it is also available in the positive z direction only, but it is oriented in the positive y direction. This is the change you have to take. And we know that the intrinsic impedance of the medium 1 is given by eta 1, that is equal to ei naught by hi naught, or ei by hi. So hi can be written like this, ei naught by eta 1. So hi naught I am replacing with ei naught by eta 1 and e power minus j beta 1 into z y cap. So like this I am writing the expression for ha bar. Further I am going to define now very important thing, that is gamma. It is a reflection coefficient. Reflection coefficient, that is the ratio of the incident electric field to the, that is the ratio of reflected electric field to the incident electric field. And then T is nothing but transmission coefficient. Transmission coefficient, it is actually the ratio of transmitted electric field and incident electric field. Actually, our job is to get what is this reflection coefficient gamma and what is this transmission coefficient T. We are going to derive the expressions for these two after writing the equations here like this. Okay, so now you can understand that how to write this ei naught. I can write ei is nothing but from this particular gamma expression I can write er by gamma. Okay, so incident wave I'm not changing. Later we are going to write a reflected wave. So this expression I can use for the incident wave. Now for the reflected wave I'm going to write. So see carefully. So the electric field of the reflected wave I'm writing here, that is er naught into e power minus j beta 1 only I'm using because it is also available in the medium 1, but it is traveling in the negative z direction. That's why here I have to take a plus. Okay, then what is the orientation of the electric field of the reflected wave? X cap only. So this is what I am taking. Now, instead of taking er naught from this particular gamma expression, you can take here er is equal to gamma into ei. Gamma into ei. So gamma into ei naught and e power plus j beta 1 into z into x cap. Okay, in this way I am writing the expression for the er bar. Then I am writing for this HR bar. So HR bar is equal to HR naught into e power, because it is traveling in the negative z direction, it is plus j beta 1 into z. But what is the orientation of the reflected magnetic field? It is in the negative y direction. You can able to see here. We have already given the expression, given the reason for this one. The reflected magnetic field is available in the negative y direction. Okay, you have to focus here. Then because of that reason I will take here minus y cap minus I am writing here. Okay, similarly now it is equal to, how to write this HR naught? HR naught can be written as er naught by eta 1. Okay, so e power plus j beta 1 into z into y cap. Again er naught can be written as gamma into ei from the previous expressions only, by eta 1 e power plus j beta 1 into z into y cap. Okay, so from this expression only er, whether it is a reflected electric field, we have to take here gamma into ei. Okay, and this can be applicable for not only for the incident wave, can be for reflected also, transmitted also we can use, but transmitted means we have to take eta 2. Okay, that means er by hr, here et by ht we have to use. Okay, anyhow we have written hr bar like this, hr bar. Okay, these are the two equations we are going to use. These two equations we are using for reflected wave. Now for the transmitted wave, so et bar is equal to et naught into e power because the transmitted wave is traveling in the positive z direction, here minus will come, and here electric field is oriented in the x direction only. But from this particular expression, T is equal to Et by Ei, Et is equal to, I can write T into Ei. So it is equal to T into Ei naught e power minus j beta 2 into z x cap. It is the Et bar. Then Ht bar is equal to Ht naught into e power minus j beta 2 into z. What is the orientation of the magnetic field of the transmitted wave? It is in the positive y direction. Now this Ht naught I can write Et naught by eta 2 because it is there in the medium 2 e power minus j beta 2 into z into y. So it is equal to Et naught is nothing but T into Ei by eta 2 e power minus j beta 2 into z into y cap. Now this expression and this expression we are using for transmitted wave. Okay, so I am taking now just what I am doing is nothing but boundary conditions I am going to apply. So if it is the boundary, here we have incident wave and reflected wave. Here we have transmitted wave. So according to the boundary conditions, we know that tangential components of the electric fields in the medium 1 and the tangential component of the electric field in the medium 2 both are same. It is always true. It is always true. Okay. But Ht1 is equal to Ht2 I can write whenever the boundary is not having the current. That means current free boundary. We'll assume this one. Current free boundary. Then Ht1 is equal to Ht2. So now we are going to apply this one. So from Et1 is equal to Et2. In the medium 1 we have two electric fields and in the medium 1 we have two magnetic fields. That is nothing but Ei plus ER we have to take in the medium 1 according to this expression I am writing. But this side we have Et only. Okay. So and boundary conditions means it is to be applied at z is equal to 0. Z is equal to 0. So now you go to Ei. So in the Ei, what we can write? Ei naught we can write. By taking z is equal to 0 from the first expression, you can see this one. If you take z is equal to 0, the remaining part is just Ei naught only. If you take Er, we will be having by taking z is equal to 0, gamma into Ei naught we can write. Gamma into plus gamma into Ei naught. It is equal to, in case of the transmitted wave, what is the E bar? We have gamma T into Ei naught. And you can take z is equal to 0. So you will be getting only T into Ei naught you will get. T into Ei naught. So Ei naught you can take left side common. Ei naught will be cancelled. So that we are getting the equation 1 plus gamma is equal to T. This is one result. Okay, you can take this is equation 1. Okay, now coming to the second boundary conditions, Ht1 is equal to Ht2. Using that one, Ht1 is equal to Ht2 I am taking. Using this one, what is the Ht1? We have to take two magnetic fields in the medium 1. One is related to incident wave and second one is related to reflected wave. So, you can take this one Ei naught by eta 1 and minus gamma Ei naught by eta 1. Ei naught by eta 1 minus gamma Ei naught by eta 1. It is equal to Ht2. Ht2 is nothing but, we are getting like this, T into Ei by eta 2. T into Ei by eta 2. And you can take Ei is common in the left side and that will be cancelled. So that what we will get? 1 minus gamma by eta 1 is equal to T by eta 2. Okay. T from 1 T is equal to 1 plus gamma. You can substitute that one. So what will you get? 1 minus gamma by eta 1 is equal to 1 plus T. 1 plus gamma. 1 plus gamma by eta 2. Just to cross multiply this one, write expression for the gamma. Okay. So what will you get? Eta 2 minus gamma into eta 2. It is equal to eta 1 plus gamma into eta 1. Then eta 2 minus eta 1 by eta 2 plus eta 1, this is nothing but gamma. So we have got the expression for the gamma in terms of the impedances. But we know that T is equal to 1 plus gamma, that is equal to 1 plus eta 2 minus eta 1 by eta 2 plus eta 1, that is equal to 2 times of eta 2 by eta 2 plus eta 1. So finally, T is equal to 2 times of eta 2 by eta 2 plus eta 1. This is the expression for transmission coefficient. Okay, so once if you see, gamma is equal to eta 2 minus eta 1 by eta 2 plus eta 1. What is the meaning of this one? If eta 2 is equal to eta 1, then gamma is equal to 0. That means no reflection, only transmission. That is what you can able to understand. Okay, so it is very important expression, and impedance is nothing but you can use the formula square root of mu by epsilon in case of perfect dielectric. That means wherever sigma is 0, you can take this particular expression, and eta 1 is nothing but all ones you have to take, and eta 2 is nothing but related to medium 2 root of mu 2 by epsilon 2. For most of the materials, mu 1 is equal to mu naught into mu r, so that this mu r is 1, mu r 1 otherwise, mu r 1 is 1. Okay, that means mu 1 is equal to mu naught only. Okay, and similarly we can take this one also, because mu r2 is equal to 5. For most of the materials, this is true. Okay, so that this thing we can write only in terms of the permittivities. Okay, so what will you write here? Gamma is equal to root of mu r2 by epsilon r2 square root of mu 2 by epsilon 2 minus root of mu 1 by epsilon 1 by square root of mu 2 by epsilon 2 plus root of mu 1 by epsilon 1. Like this you can write. Okay, so further you can able to simplify this one by taking mu r1 is 1 and mu r2 is 1. Finally, you will get the expression only in terms of these permittivities. Okay, thank you.